We defined a representation of the symmetric group on these tensor products like this. We said the P permutes the factors in here, and we have to do it in this way, that we act with the inverse permutation on the indices down here. Then we get a representation. And now let's say we choose a basis for our vector space V. This here lives in the n-fold tensor product of V with itself. And we just call the basis vectors here J, run from 1 to capital N, the dimension of V. Now with the basis of V, we can form a product basis of V tensor N. These guys here. Just choose any of these for each of the factors here, and I want to call them J1 to Jn, fewer tensor product signs and so on. So this is our product basis. And now what does a general element, a general element, let's say X in V tensor N look like? That's a linear combination of these basis vectors here. I wrote them like this once more. And here are the coefficients, and the coefficients have n indices again, and I don't write out the sums, so we sum over repeated indices. Now, how does the P act on that? Well, we just copy the coefficients, x index j1 till jn, and then we have the basis vector j1. No, not j1. We have to transform the basis vector, so it's j index p inverse of 1 up to j index p inverse of n. Okay, but we sum over all these indices. So there's a matching index for this one somewhere in here, and we can arrange them such that we write j1 to jn here again, and then we have to rearrange the indices on this coefficient x. So that's j index 1 up to jn. And now how do we have to rearrange them here? Here we really use the permutation itself. So it's indices j1, jp of 1 till jp of n, the indices on the coefficient here.